Welcome to the third tutorial in my RISC-V, Assembly Language and Architecture series. Tutorial 1 covered the basic architecture of RISC-V. Tutorial 2 discussed simulation, emulation, and cross-compilation, specifically looking at CPU later, QEMU, SPIKE, and RARS. This laid the groundwork for the remaining tutorials. Today's tutorial covers GNU tools. We'll talk about how to assemble files, how to link them, and how to debug them. We'll also look at reverse assembly using OBJDUMP. We'll interact with memory using store and load instructions and also look at how to output data to screen and how to input data from the keyboard. The first topic we'll talk about is the assembly process. The assembler's main role is to convert the programmer's readable assembly instructions known as the source code into the corresponding binary machine code instructions. We call this output code an object file. Object files have the .o suffix. A disassembler performs the reverse task then, and will convert the machine code instructions that we've just generated back into the source assembly language. The assembler also has some additional responsibilities. It understands pseudo-instructions and also directives, which can define and place data into the computer's memory locations. We could also set up a number of text strings in memory and reserve buffer space. The most common directives will be introduced as the tutorial progresses. After we've generated the binary object file, we need to link this file to form an actual executable program. The linker can act on a single file or multiple files. There may be references from one file to another, and the linker will reconcile these references. It will also decide where to allocate the memory for running the program. Memory addresses can be loaded from memory into registers and then stored back from the registers to the memory. These operations are performed with respect to memory. So loading from memory to register is a read operation and storing data from the registers to the memory is a write operation. The tutorial will use a number of short programs to illustrate how to communicate with memory. We're going to use the GNU GDB debugger extensively. This tool allows us not only to debug our programs but also to understand the program flow. We can look at program execution, instruction by instruction to see how the registers are affected and how the memory changes. We can look at the memory in different formats depending on what the nature of our data is, such as hexadecimal format, decimal format, floating point format, or we can look at them as alphanumeric characters. So the first program we're going to look at is a basic addition program, and this is narrated in the actual running of the code. So we won't talk too much more about that just yet. We're going to use system calls along the way, and these are calls to the operating system that will ease the coding burden. So for example, when outputting text to screen, it is a cumbersome process in assembly language without the corresponding helper syscall function. To output text we have to do some preparatory work, which involves setting up 3 registers. These are the argument registers, A0, A1, and A2. The first parameter we have to store is the value 1. This tells us where the text should be displayed. In this case, it'll be the output device, standard out. We then have to load register A1 with the memory address of where the output text is stored. And then finally, in A2, we're going to load the character count of the output text. Here's a basic program that we will use. This program sets up the string hello RISC-V, and then we'll use the output code to print it. And, again, we'll use GDB to single step. If we want to input data, it's fairly similar. We have to use the same 3 registers. In this case, though, to input data from the keyboard, we load A0 with the value 0. For A1, this is where we're going to store the address of the buffer. So when we read in the data, it will be located into this storage buffer. And then A2 will contain the count of the input characters. So, we want to make the buffer large enough to contain this inputted data. Here's an input text program. It's actually a little bit longer than the previous listing. We have a data section where we allocate a very small buffer. In this case, only 2 bytes of data. We'll define an input prompt, which will display, "Please enter 2 digits." The output heading will output the text that you entered. And this will print the inputted data. And then we'll have a new line character. We'll set up some more directives. This one equates the length of the input prompt to be 24 and the length of the output heading to be 14. Then we'll get into the text section, which is where we have all the actual instructions. So this program listing runs this way, and then the remainder of the program is listed here. And, again, we'll run this with GDB to show what happens. Now, something we'll talk about later on, but not at the moment, is to run this with a new assembly command option-mno-relax. So we want to use non-relax code, and we'll talk about that again as I mentioned. So it's important that we run with this option during assembly. So far, we have been using GDB out of the box, but we can make it a little more user-friendly. And if we put in these commands shown, we can get some nice windows where we can see all the registers at a single glance in a different pane as well as the source code. So by setting up these commands up in our home directory, then we can have a better experience from GDB. OBJDUMP gets the source code back from binary to source, and we can use this option-D. There are 2 main ways of doing it. First, we'll use the no aliases option so that we can actually see how the pseudocode resolves as well. Now if we use the alias by omitting the no aliases instructions, then we're going to show the pseudo instructions. And these translate into 1 or more actual native machine code instructions. We can decide whether we're going to use OBJDUMP with or without the no aliases option. Translation of aliases is one of the other jobs that the assembler performs. So here's an example. If we run OBJDUMP and we use the no aliases option, then this is what we have here. And if we use it without specifying no aliases, then this is what we'll have in this case. So what actually happens here is that things are a little bit different. We can actually see the LI instruction, which is load immediate. Now this is a pseudo instruction that actually translates into, again, as we said, 1 or more instructions. In this case, it's going to be fairly straightforward. This load immediate will translate across into add immediate. Then we look at the add instruction. And then load immediate here translates into add immediate A7 with a 0 and 93. And, again, we're going to go through a little bit more complexity in a moment. So, in this case, where we load numbers larger than 12 bits, we have a bit of an issue. If you recall from tutorial 1 that the I-type instruction uses 12 bits for the immediate field. So if we load a value like 2049, it exceeds 12 bits. If load the T0 register, that translates across to add immediate. That's fine. But when we look at the next instruction 1 loading the T1 register, we have to do this in a couple of stages. First of all, we have to do the LUI instruction, which again was mentioned briefly in tutorial 1. This will load in the value 1 and shift it over 12 places. So it'll actually be in the 13th place. And then for the second part of it, you can see T1 is invoked again. We actually add in the minus value of 2047. So this is using signed arithmetic. The first instruction sets bit 12, which is 4096. We're going to subtract 2047 from it, and this will give us the actual value 2049. So, When the immediate data is less than 12 bits, we're able to do it in one instruction. But if the immediate data exceeds the 12-bit magnitude, load immediate translate into multiple instructions. To start, we'll create a simple basic assembly program. I've already prepared it, but the commands, as you can see, listed here. So the first section shown is the text section, and this is where all the instructions will be. Our entry point for the program is at _start, and this is where the program will commence execution. The first instruction is add immediate T0x020. Now to break down this instruction, basically the format is we add a value, which is a 12-bit immediate number to a register, and then we put the result in the destination register, in this case T0. But if you recall that x0 always returns 0, so what we're actually doing is adding 20 to 0 and putting the result into T0. This is an I-type instruction. We do the same thing with T1. So now T0 holds 20, T1 holds 15. Next we add these two registers together. This is a register or an R-type instruction, and we put the result into the destination register T2. The next instruction loads register A7 with the value 93. The value 93 is the exit system call, and similarly, we're adding 93 to a value of 0 and putting the result into register A7, and then we call it with eCall, and that will terminate the program. So, let's save that program. Now the first step is to assemble it, and I'm going to assemble it with the -G switch. This means that we can use the debugger with it. It'll contain debugging information for us. So later on, when we see how it runs with GDB, we'll be able to follow along. The format is that we specify the object file first, and that's followed by the assembly source file. So the command is as for assembly-g, and then the object file is going to be listing tutorial 3-01.0. and the source file is going to be listing tutorial 3-01.s. Silent output is expected if there are no errors. Next thing to do is to link it. So, again, it's a fairly similar syntax. The linker LD uses -O. And we're going to give the same name to the executable file. The file that we want to link is the object file that we created from the assembly process. Again, silent output is a good sign. If errors are encountered, there will normally be output containing more information. Okay. So that doesn't really show much if we run it. Did the program actually work? To see what's going on, we're going to use the GDB debugger. We will call the program with the GDB command. There we go. And that started up the debugger for us. The next thing to do is to set up a breakpoint. We can break at the beginning of the program. Like that, and then it stops. So if we type the run command, it will halt at the breakpoint. Now you can see that we have the first instruction here, add immediate T0x020. To execute that, we hit End for next, and now we can have a look at that register. So if we do info, note that I is short for info, R for register, T0. And you can see that we have the value 20. So this value on the left is hexadecimal, the one on the right is the decimal value. We'll hit next to go for the next instruction, and this time we'll look at register T1. We can see there's 15 in it. Hit next and then the contents of T1. And the contents of T0 are added together with the result stored in register T2. Now if we issue info reg T2, we can now see it has the value 35 decimal, which is indeed what 20 plus 15 equals. If we hit next, then we're on to the system call. Now if you enter info registers but don't give it any arguments, it will print all the registers out. So we can see T0 has 20, T1 has 15. We can see T2 contains 35. Then we used register A7, which is where we place values for the system calls. And later on, we'll be using that for other functions such as outputting text to screen or maybe inputting some data from the user from the keyboard. We'll be using that quite a lot. So let's exit from that. We type in the Q command followed by Y for yes. So let's edit the next program. Tart outputs a text string. In the text section, we have all the instructions. Our entry point is _start. And we have to load these 3 registers with the parameters. The first parameter is one that goes into A0, the value 1 corresponds to the output screen or standard out. Register A1 is loaded with the address of the data that we want to print out. So the address is located at the label message, which is defined in the data section. The address of message is where the contents of the string are. So if we look at the string, it says, hello, RISC-V, and then it's terminated by the new line character. And then the third register we need to load is A2, and we need to store the message length there. So if you count up the characters here including the new line, that's a message length of 12. Then we invoke the 64 system call, and that corresponds to a write. And after that, we exit. So let's save that program. And we'll assemble it using the -G switch as before. Then we need to link it. And then finally we can run it. And there it prints out the string hello RISC-V. Next let's have a look at this with our debugger. So set in a breakpoint again. And run. The first instruction is load immediate. That's straightforward enough. Hit next and again. So now we have loaded the argument registers A0, A1, and A2 with the parameters expected for the write syscall. A0 registers, we can verify with the info registers command and that will print them all out. So there's the value 1 in register A0, then A1 holds the address of the text string that we want to print out, which incidentally is at 11108 hexadecimal, and then we have 12 for the character count in A2. So if we enter next, and next again, you can now see that the string hello RISC-V has been printed out. Next we can look at the memory. So we noticed earlier that A1 contained the address of our text and that was the memory location message which we reconciled to 11108 hex. So if we use the command x/, the number of bytes we want to show, which in this case will say 16. B for bytes, and then the address is going to be 11108. So we can see here some values. These are actually the ASCII values for this text that we outputted. But we can make it even easier. We can type in x/16 and put in C to display in character format. We give it the message location again, 11108. And now we can see beside the values, the text characters. So 72 corresponds to capital H, 101 corresponds to E, and so on. These last few characters here are not defined because if you remember, our message was only 12 bytes in length. We decided to show 16 of them. Now we can look at an individual character. So if I type in x/1, C, and then I'll put in the character address 0x111 09. Then we see the second letter in our string because we increment the message address by 1, so instead of the starting address of message at 11108, we issued the address 11109. This means that we're looking at the second location of our message string. And we decided when we said x/1, we only wanted to show one character. Note that the string starts at the lower address and then increases upwards through memory. If we enter x/4C0x11110, then we start at location 11110, and we just show 4 of the characters. The commands that have been used so far for assembly and linking have worked well enough for our situation. However, when multiple files are invoked, it is more usual to use a build tool to accomplish this function. The make utility will keep track of what has been done and will only apply actions to the changed portions. The instructions are conveyed to the make utility using a makefile. The makefile described can be used to assemble and link the program, test program. So let's see an example. In this case, we're going to use make to generate a small piece of code called test program. First of all, let's just look at that code. It looks pretty simple. It sends text to the screen stating this file is using make. Let's have a look at our make file. So this is our goal, here at the top. We want to generate a test program, and this depends on testprogram.o. And to generate that, we use the ld command as before. But to link the object.o program, we first need to generate it from testprogram.s. So we use the assembler using testprogram.s to generate the .o file. So, really, we're starting from the bottom and moving all the way up, satisfying dependencies along the way. When we type in make, it looks for and calls the makefile. You can see the makefile commands here. Ensure that tabs are used for indentation. Now if we issue ls, you can see that we generated the necessary .o and the output file here. If we run make again, you'll see it states that the test program is up to date. If we delete test program and then run make again, this time, it only invoked the linker because the object file was still present and up to date. Next we'll look at another make file that's a bit more versatile. We can pass the name of the assembly program that's to be executed into this make file. So let's have a look at that first. We have a variable here called target file, which is $target file. This is the name of the file that we're actually going to pass into the make file. So, if you look at the assemble string, we use the debug option -g, and we use the variable name, which again is the file that we passed, use .o for the generated object file, and then use .s for the assembly source. We have a printout here just to let us know the status. And then we do a similar thing with the linker, designating the executable, followed by the object file itself. And, again, we have a printout string. So to show the makefile in action, we enter the command make target file equals test program, where test program is the program name that is being passed. And it tells us everything's up to date. Let's have a look with ls test program. We'll remove the executable. Remove test program. We'll also remove the object file as well. Now let's invoke the makefile again. And this time, you can see it performed the assembly, and also the linking. Now, this time, we'll remove test program, but not the object file. So if we run it again, you'll see that all it does is invokes the linker, not the assembler, because we left the object file intact. Makefiles can be versatile and complex. See the reference given earlier for more information. Also ensure that tabs are used for indentation, not spaces. The final program that going to look at in this tutorial is input from keyboard. Looking at listing 3-3. We can see that we have a data section here. I've reserved 2 bytes of memory. This is where we'll input 2 characters. From the keyboard, there'll be a prompt to enter these 2 characters, and then there'll be a printout of confirmation of what was entered. Some of this is familiar from the previous program. The main difference really here is that in A0, for input, we're going to put in a 0 rather than a 1. You may recall that when we wanted to output text, we put a value of 1 for standard out into A0. The other difference for reads is that we use system call number 63, and for writes, we use system call number 64. Otherwise, it's straightforward enough. So to enter that code, we'll have to assemble it. And I mentioned earlier that we need to use the no relax option. So let's put that in here. And now, let's link it. Running the program asks us to enter 2 digits. We'll put in any 2 digits. I'll do 67. And the program just confirms that we did indeed enter 67. So, again, not terribly involved this program. It just really shows you how to input text, and there's no validation or anything like that performed. And that's the end of our tutorial. So hopefully, this will point you in the right direction to start programming using RISC-V assembly language. The next tutorial will cover arithmetic and logic instructions. Again, many thanks for watching. Links to these tutorials and companion PDF books can be found at the website risccomputing.com. See you in tutorial 4.